All right. Thermochemistry, the metric or SI unit of energy, which we use for heat, is joules. And the calorie, sometimes you see that in a problem. The calorie, 1 calorie equals 4.184 joules. How are they related? Okay, well, they equal each other. And you can use them, of course, if you need to convert between the joule and the calorie. So, in order to convert, it's just a quick little dimensional analysis T-chart, if you'd like to do that. 4.184 joules goes on the bottom to go to calories. They equal each other, so we would set it up that way. Or for the other one where you're starting with calories and you're going to joules, that means calories would go on the bottom, the 1 on the bottom this time, and the 4.184 would go on the top. It's a simple division. At the top one, a simple multiplication. Each answer would require 3 significant figures since they both start out with the measured value that has 3 significant figures, and we would go from there. So you can calculate it and check your answers, or write these down to check your answers to make sure you get the correct calculation. But simple conversion, no problem here. 102 calories for the first one and 1150 joules for the second one. Now let's talk some specific heat. Specific heat, this is unit 1 because this is a physical property of any substance. It's the amount of energy needed to raise 1 gram of the substance 1 degree Celsius. So you're warming it, okay? What is the specific heat of water in joules and in calories? These values you are supposed to know for the SOL, 1 calorie per gram times degrees Celsius, or 4.184 joules over grams degrees Celsius. These guys, of course, are for water, H2O, okay? And other ones, if they require you to use specific heats of metals or anything else, they usually supply that number for you in the problem. Or they'll give you a little table that has a bunch of them on there, and you have to pick out the correct one to use in the problem. Okay, so all appropriate units, this is a derived unit, is an energy unit over the grams times the degrees Celsius. We use that in our Q equals MCAT equation for cancellation purposes. Which brings us to that lovely equation. I believe that's next. Oh no, let's actually look at some tables here. Like I said, they could insert some tables where you have to pick it off. So from the table, identify the substance with the highest specific heat capacity. And look, they even have specific heats for the different phases of H2O. We have the liquid water, we have ice, and we have water vapor or steam. So each phase has its own specific heat value, as you can see up there. And then they list out some other ones along with some metals here at the bottom. So which one has the highest? Liquid water, and which ones are the lowest? Which ones? Gold and lead, yes, are both 0.129, very low specific heats, and metals have very low specific heats because they heat up very quickly. They absorb heat. And so if you put two pans on the stove and you filled one with water and left one without water, the one without water you wouldn't be able to touch in about 30 seconds. The one with water, though, it would take a good 5 minutes depending on your efficiency of your stove in order to get that water heated up. Water absorbs a lot of energy before it's actually going to change its temperature. Okay? So, high specific heat of water is due to blank forces of attraction known as, what are the forces of attraction for water? Anyone? It is a polar molecule, but what are their intermolecular forces of attraction that hold water together? So I can have a glass of water or a bottle of water that hold all those waters together. It would be hydrogen bonds. So we have 3 different forces. We have London dispersion forces, dipole-dipole, and hydrogen bonding. What is significant about hydrogen bonding in comparison to the other 2? Stronger, yeah. So water, due to the strong forces of attraction known as hydrogen bonds. That gives water a lot of really unique properties, those hydrogen bonds, right? So now we're going to look at using our Q equals MCAT equation again. This we used at the very beginning of the year in Unit 1. And this is for warming of a substance. The Q is the heat, the M is the mass in grams, C is specific heat. Like I said, you have to know the water ones, the other ones they'll give to you in the problem. And delta T is the change in temperature, the final minus the initial. So it simply is a plug it in and calculate it out. So if I have 40 grams, I have 10 degrees going to 30 degrees. That's my final and initial temperatures. And then since this is water, I have it on my table, but I could look it up, the specific heat to plug in. Plug it all in. What you should notice here is that the grams will cancel with the grams, and the degrees Celsius cancels with the degrees Celsius. So I do end up with my joule here, which is what I want because I need a value, a unit that goes with heat. Also, when I'm doing significant figures for this, I would use the measured values right here. The specific heat, though, is more of a constant, so we wouldn't really calculate that in. All right, so here, 40 times 4.184 times 20, basically, once you do that subtraction, that change in temperature, then you would end up with 3,350 joules. There's usually one Q equals MCAT or one heat of fusion, heat of vaporization problem that you'll see on the SOL. They aren't hard to do. They are pretty simple. However, they can give it to you where they don't give you mass and you have the other three variables, or they can give you to solve for specific heat, the C value. So any of the variables they can have you solve for, you just need to make sure you plug them into the correct spots. Okay? Q equals MCAT. For this example, what mass of silver can be heated by the 3,000 joules there if the temperature increased by 35 degrees. So once again, you would set it up. But in this particular case, the mass is the one that's missing, and that's what you would solve for. You would use your algebra to solve for it. Once again, you would see cancellation of units. Joules would go, and then of course we end up with our gram unit, which makes sense because we're trying to find a mass anyways. And then when you do all the algebra and divide and multiply, you should end up getting 365 grams. Does that make sense? Yes. Pretty simply put. Review, like I said, Q equals MCAT. This is the warming equation. We also use it for our heating curves, which we're about to go back over real quick. The heating curve here, A, C, and E, they are all the slopes on the heating curve. This is where our substance is warming. It is not phase changing here. Solid is warming at A, the liquid is warming at C, and at E, our gas is warming. That means I'm adding in heat. It's raising the 1 gram, 1 degree Celsius based off of the specific heat. And it's increasing their kinetic energy. They're starting to move faster. How do I know they're starting to move faster? Because the temperature's increasing. Temperature is a measure of the average kinetic energy of the particles. So as the kinetic energy is increasing here, the particles are starting to move faster. So in a solid, they're still in their fixed position because the intermolecular forces are holding them together, but they start vibrating a little faster. And as they get closer to that melting point, the melting point, which happens to be here at 0, then once it hits that point, it can start overcoming the forces and start spreading out. So yes, B and D are the plateaus. They are the phase changes here. Melting and vaporization. Now I do want you to note that the plateaus also tell you the melting points, MP, and the boiling point, the BP. That tells you those particular pieces of information. But also the size of the plateaus, as you can see, are different. The melting plateau is very short. The vaporization one is very wide. When you melt something, you overcome some of the forces, so it spreads out a little bit and becomes a liquid. However, by the kinetic molecular theory that you just learned in the gas laws, when it becomes a gas, it's supposed to not have any attractive forces anymore. So all of the intermolecular forces need to be overcome to reach gas phase. So that's why those plateaus are a little bit longer, because it requires a whole lot more energy to overcome all the forces rather than just overcoming some of the forces. Phase changes. This is the new part. It's a T-chart though, it's not very hard. Molar heat of vaporization versus molar heat of fusion. And it's written like this, it's a delta H vaporization, delta H of fusion. And it is defined as the molar heat needed to change 1 mole from a liquid to gas for vaporization, and then the amount of heat needed to change 1 mole of a solid to a liquid. Okay? So fusion versus vaporization. Now, the vaporization magnitude amount is also applied to condensation. Condensation is just the opposite of vaporizing. So instead of adding in heat or absorbing heat to vaporize, now you're releasing heat in order to condense. But it is the same magnitude of number. So if they ever ask you to condense something, use the vaporization number. If they ever ask you to freeze something, use the fusion number. The fusion number goes with melting and freezing, and the vaporization number goes with condensing and vaporization. So, just a different direction. The heat is being released rather than being absorbed. They will also give you this information. You are not expected to memorize any of the delta H vaporization or fusion numbers. They will provide a table like so, or they'll actually write it into the problem for you. So you will not be expected to know these. I will put it on my quiz as well so that you'll have the table of values to use at your disposal. The problem is you need to make sure you select the correct one to use. Okay? So, you're going to set up a T-chart because usually they're going to start with grams. And you have to change it to moles. And since the vaporization and fusion numbers are in kilojoules per mole, we need our value in moles to use. So we're going to use the correct one from the chart. So let's do an example and show you what that means. Calculate the heat required to melt 125 grams of ice. Well, that's my starting amount, and ice is what compound? H2O, very good. So before I can do anything else, though, I need to change my grams to moles. And does anybody remember the molar mass of water? 18.02? Yes, okay. Now the key word up here, though, is it says melt. So which one am I using, vaporization or fusion? I need delta H of the fusion. What number is that number for water? 6.01. This is kilojoules per 1 mole, by the way. So we're going to use this as a conversion factor in our T-chart. So what can I do with this mole here? I'm going to diagonal it down. I put moles on the bottom, and I put the 6.01 kilojoules on the top. Now it's going to cancel nicely. Do moles with moles, and I do grams with grams, and then I'm left with my kilojoule, which is what I want. I want a heat measurement. Okay? So make sure you change your grams to moles. Make sure you use the correct delta H if it's vaporization or fusion. So spend a moment to look at that. Here we would have gotten 41.7 kilojoules. Now try a few of the other problems and see if you can do them. Pay attention to the substance and pay attention to what phase is it occurring so you know which delta H to choose. Okay, so let's take a look at the next one, see if you set it up right. This one, boiling water. So you should have picked the heat of fusion number. This is delta H. Vaporization, you still change it to moles first, then you use that. So that's a delta H vaporization of water. So check that one real quick. Okay, let's look up here at the next one. So this one, you had to calculate ammonia. So remember, ammonia is NH3, so this is your new molar mass. Also, it says freezing, so we wanted the delta H of fusion here for ammonia, which is 5.66 kilojoules. So this is what you should have ultimately got for this one. Now try the next one because it is the most difficult. It's the one where they have you work backwards. Now, looking at the last one, you're starting out with the kilojoules. So, this is what you have to think, work backwards. So the kilojoules go in the upper left corner. Then you diagonal down the kilojoules right here and go to 1 mole, using that as the conversion factor. This is vaporization, so you should use the one that's 38.6 kilojoules per 1 mole. But you can still flip that and use it as a conversion factor. And then, of course, this is ethanol, so it's C2H5OH, which gives us this molar mass right here. So when you calculate it, the kilojoules will cancel, the moles will cancel, and that takes you back to grams. So it's basically just working it backwards. So take a moment to look at that. All right, so moving on, let's take a look up here. Looking at the different parts of the heating curve, which should you use at each particular one? Well, anytime you're warming, you're using Q equals MCAT. You're raising the temperature by using heat. That's basically what you're doing there. So A, C, and D, no, I'm sorry, A, C, and E, those ones are all going to be Q equals MCATs because that's warming it, changing the temperature. Now remember, the plateaus, those are phase changes. They have this equation here as Q equals moles times the heat of fusion, but like I said, you usually give you grams there instead, so you have to change the grams to moles first. That's why it's easier to do it in a T-chart. So I like to use dimensional analysis here, do the grams to moles, and then you use the heat of fusion to change it over into kilojoules. That also applies here at the vaporization. And do remember too at the phases here, the energy is being used to separate them, to overcome the forces. It's not trying to make them go faster. That's why it is a plateau, and that's why the temperature is not actually changing. So keep that in mind. So once again, the generalized formula is mole times the heat of vaporization there, but usually they give you grams to start with, and then you have to go from there and change it into moles before you can multiply it. Okay? So these are where you would use the different thermo equations as you're going up the heating curve. Any questions on that? All right, so let's take a look at our phase diagram. Let's review that because they might have one of those on the SOL. Everybody remembering the triple point? The one where there's all 3 phases coexisting at one time and they keep changing. Dynamic equilibrium once again. Critical points up here, that's where we end up with supercritical fluid where it's not really a gas or not really a liquid anymore. But it also has temperature, pressure values here. So all the different phases at different temperatures and pressures so that you can figure out stuff. Usually they don't label the solid, the liquid, and the gas for you, but that's where they are located in this Y-shaped curve. Solid is on the left, the liquid's in the middle of the Y, and then over to the right is the gas. So that tells us that this line right here is going to be which phase changes? We have sublimation, yes. Going from the solid to the gas, we have deposition. Going from the gas to the solid. How about this line right here? What phase changes occur here? Melting, yep, and freezing. Very good. Melting and freezing. Now at different pressures and temperatures, of course. The last one over here, this line that's between the liquid and the gas, didn't draw that very well. Hold on a second. Staying with the line there. Going this way, it's going to be what? Vaporization, we're making the gas. Okay. Going this way, it should be what? Condensation. Now these are usually very easy read the graph kind of questions, just making sure you know where everything is on the graph before you get questioned it. So let's do a few examples here using our phase diagram. Where would the triple point be if we're looking at this graph? About 51 or so ATM, that's fine. Now I know question 2 seems kind of stupid, but they could phrase it that way instead of number 1 where they actually asked for the triple point. Number 2 they're asking for where all 3 phases coexist. which should be at the triple point. So make sure that you understand those points together. So it's still 350, 51 ATM here. Now it's reading the graph time. What phase change or phase changes occur when it's heated from 100 to 400 at 40 ATM? Well, that's all I do is I come over here, I do that, go to my 400, going that direction. What phase change is it? Sublimation. See, not too difficult, right? Pretty easy stuff. Just review. We did do this back in, September, October time. Sublimation. Okay. So approximately, that would be the good ways to read off of the diagram here. A few more practice real quick before we move on. What phase change or phase changes occur when heated from 100 to 450 at 70? Well, I go up here to 70 and I'm at 100. Now I go to 450, which is somewhere right here. What phase change would that be? Melting. Very good. What phase change occur when we're cooling it from 700 to 500 at 60? So starting here at 700, going to 500, that away. What phase change is that? Condensation. And the last one here, we are starting at 70 again, 700, but we're going all the way over here to 300. So in that case, we have two phase changes. What are they? Condensation and then freezing. Very good. So easy to read our lovely phase diagram. Condensation and freezing. Okay? Now for the really fun part, reviewing intermolecular forces and polarity and shape stuff. Because what you don't probably realize is, yes, we did that back in Unit 4, but intermolecular forces tell us a lot about different properties for the chemical itself. Nonpolar and polar. Remember nonpolar, they're equal sharing. They have a symmetric shape. Oops. Polar is where there's an unequal sharing and you have an asymmetric shape. Okay? So, unequal and equal. Nonpolar is equal. Polar would be unequal. And remember, even in solutions, like dissolve like, the polar stuff would dissolve polar and ionic that have charges. Nonpolar would only dissolve other nonpolar things that have London dispersion forces only. So like does dissolve like. That's another application of our polar-nonpolar stuff. Now looking at symmetric versus asymmetric, this is boron trifluoride. It is trigonal planar. It has the boron, remember, only needs 6 valence electrons here, but it has a symmetric shape, so any kind of dipole moments end up canceling out. So this would be nonpolar, and it's only going to experience London dispersion forces. Whereas, say, something like water or carbon monoxide, these two examples, both are polar, either due to the shape with the lone pairs causing it to be bent and then therefore not symmetric, or CO, where you have two totally different atoms. The difference between them, of course, is higher than 0.5 on the electronegativity difference, and therefore also polar. Now let's determine shape and determine polarity. Does anybody remember the shape on, say, ammonia, where you have 3 ligands attached in one lone pair? What is that going to be? Trigonal. It has the one lone pair, so what does that do to the other 3? It pushes them downward, right? So it forms the pyramid. This one's going to be trigonal pyramidal. And since it has a lone pair, is it polar or nonpolar? It's going to be polar. Yes, it's going to be asymmetric. How about fluorine, where we only have the 2 atoms? What shape must that be? Linear. And do we have symmetry here? Yes, so this one is going to be nonpolar. Good. So pyramidal and polar, and linear and nonpolar. Okay? So keep that in mind for these particular ones. Go ahead and try the next few. We have hydrogen chloride, we have water, and we have methane, CH4 here. What would the shape be on hydrogen chloride? We only have 2 atoms, so that one would have to be linear as well. Now, since they are different atoms, then it should be what? Polar. How about water here? What shape is the water molecule? Bent, our favorite one, yes. And due to the lone pairs in the bent shape, is it symmetrical? No, so it's going to be polar. And methane, what's the shape of methane? 4 things attached, no lone pairs is definitely tetrahedral. And since all of them are the same, the hydrogens surrounding it, the ligands are the same, this is going to be symmetrical and nonpolar. Very good. So linear for hydrogen chloride, but polar since they're different atoms. Bent for water, and polar and tetrahedral and nonpolar for our methane. All righty. Now, intermolecular forces, the fun review of those. Now, the difference in properties of molecules and compounds are as a result of these attractive forces. Differences in them. The attractive forces that hold them together in ionic and covalent bonds are called intramolecular forces. So an actual covalent bond or ionic bond or metallic bond, those are within the molecule. Those are called intras. Now, intermolecular forces are attractive forces that hold identical molecules together, such as water in a drop of water or a glass of water, okay? And they are due to these intermolecular forces. We say between now. These are between molecules, not in the molecule itself, but between the molecules, between 2 waters. So like for example here, if I'm looking at these 2 waters, we have our partial negative, our partial positive. This dotted line, that's the H bond. That's the intermolecular force, IMF. What you should know too is the actual bond between the H and the O here, this one, that's a covalent bond. That's an intramolecular force. It's within the compound, okay? IMF's, the intermolecular forces, actually controls a lot of what's going on here. Now, London dispersion forces are the weakest. We know these apply only to nonpolar substances or like noble gases that have electron clouds. Remember, their strength increases as you add mass, more electrons, a more polarizable cloud, therefore a stronger London dispersion force if it's bigger, okay? Dipole-dipole forces. They are stronger than LDF, and that's because they have permanent dipoles that are polar molecules, and they line up based off of their charges. So like the partial negative is attracted to the partial positive of the other molecule, and they line up and look in that particular order. Now for water, our hydrogen bond example. It is a special type of dipole-dipole attraction, about 5 times stronger because the electronegativity difference is pretty high. And it's an attraction between polar molecules, but you have to have H bond. You have to have H with F, H with O, or H with N, or it does not work. Okay? H with F, H with O, or H with N. So now you're going to do some quick practice looking at shapes, molecules, and determining their forces. Hydrogen bonds, of course, make unique properties of water like high surface tension, high heat of vaporization, and high specific heat capacity. Those are all unique to water. Very, very interesting. Also, you could add cohesion, adhesion to the list if you really wanted to, and give it capillary action all as well. So now I'd like you to determine whether it's polar or nonpolar, the shape and the force. Go get started. So carbon tetrafluoride, polar or nonpolar? Nonpolar. What's the shape? Tetrahedral and the force. London dispersion forces are the strongest forces. How about the second one, OF2? Polar, what's the shape? Bent, and what is the largest force? It has London dispersion, it also has what? Dipole-Dipole forces, good. How about PCl3? That one's going to be pyramidal. Yes, it has that lone pair pushing the other three down, even though it looks upside down up here. So is that polar or non-polar? Polar. And does it have any H's in it? No, so its strongest force is going to be dipole-dipole. And HF over here? Polar. What's the shape? Linear. And its strongest force? Hydrogen bonding. Very good. Take a moment to review that real quick. Okay. Any questions? What does the what stand for? HF, hydrogen fluoride? Oh, London dispersion forces. That's what it stands for, yes. All right, as intermolecular forces get stronger, the more energy required to break the forces or overcome the forces holding them together. So, if you have stronger forces, your melting and boiling points will be higher. Okay? So it's harder to break them apart if you have stronger forces holding them together, which makes sense if you think about it. So let's talk about vapor pressure. I've talked about it in terms of gas laws, where it's that thin layer that forms on top of the liquid. It is evaporating and condensing at the same rate. It's in dynamic equilibrium. So as you see here, that little vapor that forms on top of the liquid. Pressure exerted on the gas in equilibrium with a solid or liquid in a closed container at a given temperature. You are going to have these vapor pressure curves, and what did they tell you? The vapor pressure curve is going to tell you basically when it can boil or when it's going to boil. So the vapor pressure at different vapor pressures, if the atmospheric pressure equals the vapor pressure, then the liquid will boil here. So liquid boils when the vapor pressure equals the atmospheric pressure. So here at sea level, we have a little bit higher pressure, but water and other substances will boil at less temperatures up in the mountains in Colorado because the atmospheric pressure is thinner up there. So the air is thinner, so the pressure is lower. Atmospheric pressure at sea level, this is standard pressure. Standard pressure, 1 atm, 101.3 kPa, and 760 torque. So here what you're looking for is at standard pressure, this would be our normal boiling point, okay? Because that's when it would equal atmospheric pressure at sea level, which we're about at sea level ourselves, okay? So, different intermolecular forces have different vapor pressures. Some have higher vapor pressures, like things that have London dispersion forces, they are weaker. The ones that have stronger forces have lower vapor pressures because they're holding on to their molecules a little bit tighter. That force between them is holding on a little bit tighter. And therefore, you're going to have a higher boiling point, okay? So to read the graph, really you're looking at the lines in the boiling points. The ones with the higher boiling points have stronger forces, like the water over here. This one's going to be a stronger force than, say, this one, the diethyl ether that boils at 34.6. So stronger forces mean higher boiling point, mean lower vapor pressure. From the graph, we can see water has the strongest, followed by the ethanol, which is the ethyl alcohol, and the diethyl ether. So diethyl ether has the weakest forces up here because its boiling point is lower. Why? It's not holding on as tight, so it's easier for the vapor pressure to equal atmospheric pressure. You just have to be able to read these curves very easily, so not too difficult to do. As you can see in the next few problems, it'll be pretty simple. What is the vapor pressure of CH3Cl at 50 degrees? Well, all you have to do is go to the 50-degree mark and go to the line. What does it say its vapor pressure is? About 70 kPa, right? What is the vapor pressure of water at 70 degrees Celsius? That one's pretty easy. That's what? 30 kPa, yes. What is the normal boiling point, though, at standard pressure? We call that the normal boiling point. So if you look at the line that goes across, the 101.3 is telling you that's where the standard pressure is. So for water, that's going to be what? 100 degrees Celsius. How about for carbon tetrachloride? What is its normal boiling point about? About 75, I think. Yes, it's in between the 70 and 80 mark. Now, which one on here has the weakest force? CHCl3, because its boiling point is the lowest, yes. Just a couple more quick things here. Colligative properties. Now, this is the basic definition. It's all dependent on the number of solute, the number of particles dissolved in the solvent. That causes vapor pressure lowering, it causes boiling points to increase or elevate, and it causes freezing points to go down or depress. We use freezing point depression in our ice cream lab, which we're going to try to do here before the end of the year. Boiling point elevation, though, increasing the boiling point, vapor pressure lowering, lowering the vapor pressure. Now remember here, I showed you, this is like a little area of vapor pressure. If you add solute particles in orange here, well, not as much is exposed to the surface, so you get less particles that are evaporating and condensing, so the vapor pressure goes down. Vapor pressure goes down, it's harder to boil because vapor pressure has to equal atmospheric pressure, so you need to increase your energy to increase the vapor pressure. Therefore, it increases the boiling point. So, they tell you to put salt in your water to make it boil faster. They're completely incorrect, because that's going to make you have to use more heat to get it to boil. So if we're looking at different substances that we put in solution, it's all dependent on the number of particles it breaks up into. So instead of making you go through this bit by bit, I'm just going to show you, if you remember your ionic soluble compounds, they break apart into their ions. So KBr should break apart into 2 particles, and you get K plus and Br minus. MgCl2 is going to break apart into 3 particles per mole, so you get 1 of those and 2 of those. Whereas the aluminum sulfate, you get a total of 5, because you get 2 Als and 3 sulfates every time it breaks apart. Glucose, though, is just a sugar molecule. It doesn't break apart. Water just surrounds it. Okay? It's not an ion. So out of these different ones, the ones that's going to have the greatest effect, if there are equal amounts put in there, is the aluminum sulfate. Why? Because it produces the most solute particles in solution when it breaks apart. Okay? So that's important there to note that the number of particles causes the boiling point to increase, or the vapor pressure to lower, or the freezing point to depress. Okay? So if I would say which one has the highest boiling point elevation, it would be the aluminum sulfate. Which one would have the least effect? The one with 1 particle. It's not as much. So that would be the glucose or the sugar. And then, of course, the lowest freezing point, or depresses the freezing point, once again, is going to be the one with the number of the most particles, 5 particles in the aluminum sulfate. That's how we would compare which one would have the greatest effect on these properties. We do have only one more little topic to discuss, and it's entropy. And we talked about entropy at the beginning of the year. The randomness and disorder of the universe and systems. And we're looking specifically at the randomness and disorders of our chemical reactions and our chemicals in general. It's a very simple, easy system to look at. It's a measure of the randomness. More arrangements, more disorder, the system has more energy, basically. More free, it contributes to the free energy that it has to incorporate into its reaction, or its ability to react. Now, solids are very orderly, as you can see, so they have low entropy. Gases have no intermolecular forces, are going everywhere. They have a high entropy. Liquids are kind of in the middle, okay? So keep that in mind. So solids have less entropy than liquids. Liquids have less entropy than gases. There's one other little thing. If you have an aqueous solution where you dissolve some solute in there, aqueous solutions have more entropy than just pure liquids. They have more randomness going on in there. Now, if you have all the phases being the same, then you start counting particles. Counting moles. So if you're going from like 5 moles to 2 moles, well, you're definitely becoming more orderly. If you're going from, 3 moles to 7 moles, you're becoming more disorderly by producing more particles. Let's look at a few examples and discuss them. So if I'm looking at this example, I have 2 moles of liquid water going to 2 moles of hydrogen gas plus 1 mole of oxygen gas. So basically 2 moles of liquid going to 3 moles of gas. Is that an increase in entropy or a decrease in entropy? Increase. So you would write delta S, the change in entropy is an increase or positive. The next one here, I have 2 liquid moles. I have 15 gas moles going to 12 gas moles plus 6 gas moles. Is that an increase or decrease in entropy? So we have 17 moles on the left, but 2 of them are liquid. We have 18 moles of gas on the right. All of them are gas. So that should be an increase in entropy. Looking here, we have 2 moles of solid plus 1 mole of gas going to 2 moles of solid. That should be a decrease in entropy. Good. Now looking here, sodium chloride is being put in solution with water, breaking apart into its ions. Is that an increase or decrease in entropy? That would be an increase. Last but not least, we have 2 moles of sulfur dioxide, 1 mole of oxygen going to 2 moles of sulfur trioxide. That is a decrease, 3 moles of gas to 2 moles of gas. Last but not least, we have liquid water freezing into ice, basically going into solid water. That would be a decrease in entropy. Good. Now, you can use this packet for studying for your quiz as well as using it on your e-carts. It would be very helpful for lots of different areas on those e-carts. So use it to study, please.